Alright, I want to go over the sample problems with you. Hopefully you read them and looked at them, but just to kind of explain a few things. Just a few things to kind of point out here before we start. We're going to be talking about forces, obviously, and a lot of times we talk about the force of weight, and the force of weight is always going to be straight down. If we're talking about a rope or a wire, it's going to have a certain amount of tension. That's also a force. So we can use those forces together. Typically, we're going to use our forces in newtons because that's the SI term that we're going to do. If we have a force and these forces are all balanced, in other words, the balance meaning that either the object isn't moving or the object is staying exactly the same. It's not accelerating, it's not slowing down, anything like that. If we have that force, I can take this angle, right? If it's at an angle, I can't figure it out. If it was like up and down, I can do that. If it's left and right, I can figure that out pretty easy. But if it's at an angle, I actually have to kind of figure out each proportion, the x component, the y component, and figure out how much that is. And the easiest way is just to draw your parallelogram. And so here's my y component, here's my x component, and we're going to use a little trig. We can use sine, cosine, and tangent to figure out those sides. If we know one of them and we know the angle, we can figure out the other ones. So that's kind of how we do a lot of these problems. So I want to work through these 4 examples with you. Some are really simple, some are a little more complicated, but let's just work them. All right, so the first one, really easy. We've got this gymnast, and he's hanging, and his total weight is 650 newtons. He's hanging by both arms, so obviously that's going to be split. Each one of those is going to be 325. All right, that, I think, is really simple. But now let's start talking about things at angles. So let's take a look at this. We've got this painting hanging on the wall that weighs 126 newtons, and it's supported by a wire, and just like you would normally hang up a painting, just like that. So, they're saying that angle between that is 90 degrees, and we want to know what is the tension or the force in each wire. The easiest thing to do is to just work with half at this. So we've got 2 different wires. We can only calculate one at a time. So let's just work with half of it. So that's what they've drawn right here. We're drawing the left half, so we're taking this part right here of that triangle. And if we take half of it, that angle is going to be 45 degrees. We've got a force, y, that's going to be the weight of this object, but it's only going to be half of the weight because one side of the wire supports half, the other side of the wire supports the other half. So in my case here, Fy, instead of being 126, it's going to be 63 newtons because that wire only has to support half. But what we're trying to figure out is how much force is actually in that wire there, how much the tension in that. And if we know an angle and we know its adjacent side, we can use cosine to figure that out. So remember, cosine is adjacent over hypotenuse, and in our example, adjacent is the Fy, and the hypotenuse is F. And we're trying to figure out F, so that's what they did here. They solved for F. Just moved it around, manipulated it algebraically, and then put in. So my Fy was 63 newtons, and my cosine of 45 degrees, which comes out to be 0.71, divided it out, and you get 89. So on both sides, you have a force of 89 newtons. Same thing on this side. So despite the fact that only one side is actually lifting up at a force of 63 newtons, the tension in the rope or the wire is as high as 89 in this example. All right, let's take a look at somebody on a swing. And so we have Michelle, and she has a combined weight of her and the tire is 825 newtons, and her friend pulls her back, so it's at 30-degree angle, and they want to know what the tension is in the rope. So, if we kind of break down, and I always suggest that you draw the drawing in physics is kind of the one of the most important things, because you got to get your drawing right to figure out everything else that's going on. All right, so here's what they're saying. Here's our force. That's the force, the tension in the rope, and the weight. The weight is always straight down, and that's going to be that 825, so we know that. Okay, And we should know this angle. Okay, we know that that's 30 degrees. That's what it said up above. So this is just another trig, a real simple trig problem. We're going to use cosine again. In this case, my adjacent is the weight, and the hypotenuse is the force. So I plug in those things, and once again, I'm solving first, I guess, for f. And when I plug that in, I get 825 over cosine of 30. And so that comes out to be 953 newtons. All right, now here's the toughest one on these examples. And really, it's tough because there's really two problems involved here. So let's take a look at it. It says, after returning home from the beach, Samantha hangs her wet 2-Newton bathing suit in the center of the 6-meter-long clothesline to dry. This causes the clothesline to sag 4 centimeters. What is the tension in the clothesline? Now, here's the thing that you got to understand. First of all, there's really two things. We're talking about some distances. That's one part of one part of it. And we're talking about a force. And you can't just create a triangle using a force and then a distance. They don't go together. You always got to use the same terms together. So we don't have an angle. So what we're going to try to do is figure out the angle by using the distances. And then once we know the angle and the force, then it's the same as the problem that we just did previously. So the first thing we need to do is convert, because we have centimeters and meters. So we convert that. And so here's their drawing of half of that. And obviously this is not drawn to scale. But what our goal here is, what we're trying to do is figure out this angle, because we don't know that. But we do know that it sags 0.04 meters, and we know that half of it is 3 meters. That's the key. We're not talking about the whole thing. We're only talking about half. And so to figure this out, now look at, we have opposite and we have adjacent. So obviously that's tangent. So tangent is opposite over adjacent. So we're talking about 0.04 over 3. So we know that the tangent of theta equals 0.013. Now, if we want to figure out what the angle is, because that's my key, I need to do the inverse function, or the reciprocal function of tangent. So you're going to hit your, however yours is, a second function or INV key on your calculator. So you're going to say second or INV tangent of 0.013, and it should give you an angle of 0.74 degrees. Check that out. Make sure you understand how to do that. That's key, that you can go backwards doing tangents too. And tangent, cosine, sine too, but all of those. All right, so now we have the angle. Now we're going to work the other part of the problem. So now we've got this force up, or really it's the force, it's the weight of that thing, and that is going to be, it's 2 newtons for the bathing suit, but we're only working with half, so that's going to be 1 newton. And we know the angle here is 0.74 degrees. And our goal, what we're trying to figure out here, is what is our force here. We don't really care about f of x. That's irrelevant to what we're trying to do. So we have an angle, we have the hypotenuse, and we have the opposite side. So in this case, we're going to use sine. So sine is opposite over hypotenuse. And we're solving for f. So that's going to be Fy over the sine. So we're going to take 1 Newton over the sine of 0.74 degrees, which is 0.013. Oh, look at that, same thing. Isn't that interesting? And we get 77 newtons for our final answer. All right, so hopefully those make sense. Go ahead and work the other problems after that.